Ever wondered how finite automata work? One key to unraveling this mystery is understanding transition graphs. You see, finite automata are abstract machines used in computer science that process sequences of symbols or inputs. They're like the secret agents behind pattern recognition, parsing, and other computational linguistics. Now, to visualize how these clever machines operate, we use something called transition graphs. These are graphical representations that help us see the states of a finite automaton and the transitions between these states based on input symbols. It's like a roadmap for how our automaton is going to react to different sequences of inputs. Whether we're dealing with deterministic or non-deterministic finite automata, transition graphs provide us with a clear picture of the automaton's behavior. So let's dive into the fascinating world of transition graphs. First, let's talk about nodes, the fundamental building blocks of transition graphs. Nodes, sometimes referred to as vertices, are the essential elements of a transition graph. In this context, each node signifies a unique state within the finite automaton, the theoretical machine we're modeling. So if you imagine an automaton as a little robot that can be in different moods or modes, each node represents one of those distinct moods or modes. Usually nodes are represented as circles or labeled points within the graph, each one corresponding to a unique state in the automaton. This visual representation allows us to grasp the variety of states an automaton can be in. It's like looking at a map of a city, with each node being a distinct location within that city. What's important to remember is that each node is unique. Just like every location in our hypothetical city has its own unique characteristics, each state in the automaton is distinct. It's not just about being different in name or label. Each state represents a unique configuration or condition of the automaton. Nodes are not just passive elements, though. Each node is part of the active process of transitioning from one state to another based on the input symbols. They are the key players in this dynamic game of shifting and changing, depending on the input they receive. In this sense, nodes are not static but dynamic, constantly involved in the process of change and transition. They are like the actors on a stage, each playing their part in the unfolding drama of the automaton's operation. So when we look at a transition graph, we should see more than just circles or points. Each node is a snapshot of the automaton's state, a moment in its ongoing journey of transitions. When the automaton receives an input and moves to a new state, it's like our actor changing costumes and stepping into a new role. So, nodes represent the different states an automaton can be in. Each node is a unique state, and together, they form the diverse and dynamic world of the automaton. A world brought to life through the language of transition graphs. Next, we'll explore the edges of a transition graph. Imagine you're on a journey, where the nodes are the destinations, and the edges are the pathways that lead you from one destination to the next. In a transition graph, these pathways, or edges, are the vital links that connect the nodes, allowing the finite automaton to transition from one state to another. Each edge in the graph represents a specific transition, dictated by an input symbol. Think of these input symbols as the keys that unlock the next destination on your journey. When the finite automaton encounters a particular input symbol, it follows the corresponding edge to the next state. Edges, therefore, are like signposts, each labeled with an input symbol. They guide the automaton on its journey, shaping its behavior and determining the paths it can take between states. The labels on these edges, the input symbols, are what trigger the transitions. For instance, an edge labeled A indicates that upon receiving the input symbol A, the automaton will move along this edge to the next state. But how does this work in practice? Well, imagine you're at a node representing the current state of the automaton. You receive an input symbol, let's say B. You scan the edges emerging from your current node, searching for an edge labeled B. Once you find it, you follow it to its end, arriving at a new node, a new state. The beauty of these edges lies in their simplicity and clarity. They provide a straightforward visual representation of the transitions between states, making the behavior of the finite automaton easier to understand and predict. By simply following the edges and their labels, one can trace the possible paths the automaton might take in response to a sequence of input symbols. In summary, edges represent the transitions between states based on input symbols. They are the pathways that guide the finite automaton on its journey, shaped by the sequence of input symbols it encounters along the way. In the next scene, we'll delve into the start state and accepting states. the specific nodes that mark the beginning and potential ends of this fascinating journey. Now, let's look at the special nodes in a transition graph, the start state and the accepting states. In the world of finite automata, these nodes have very specific roles. First, let's dive into the start state. This is the initial position of the automaton, the point from which all possibilities spring. It's like the first step on a journey, the once upon a time of our story. In the graphical representation of a transition graph, the start state is usually indicated by an arrow pointing towards it, as if to say begin here. But remember, there is only ever one start state in a finite automaton. It's a unique position that sets the stage for all the action to follow. Now let's move on to the accepting states. These are the states that indicate successful recognition of a pattern or condition. Imagine you're playing a game, and the accepting state is the end goal, the victory point. When the automaton reaches an accepting state after processing an input string, it's like crossing the finish line. It means the string is accepted as part of the automaton's language. In the transition graph, accepting states are often represented with a double circle, like a target, signifying that you've hit the mark. But unlike the start state, there can be more than one accepting state in a finite automaton. It's like having multiple ways to win the game. Each accepting state represents a different pattern or condition that the automaton can recognize. So to recap, the start state is the unique initial state of the automaton, and it's where the journey begins. The accepting states are the end goals, the points of successful recognition, and there can be multiple of them. Together, the start state and accepting states form the backbone of the finite automaton's operation. So the start state and accepting states are special nodes that play crucial roles in the operation of the automaton. Let's now discuss how transition graphs can represent different types of finite automata. Finite automata can be broadly categorized into two types: deterministic finite automata, or DFA, and non-deterministic finite automata, or NFA. The difference between these two types of automata primarily lies in their handling of transitions, which is reflected in the structure of their transition graphs. In a deterministic finite automaton, each state has exactly one transition for each input symbol. This means that given the current state and an input symbol, the automaton can determine the next state without any ambiguity. In the transition graph of a DFA, each node, representing a state, has one outgoing edge for each input symbol, and each edge is labeled with a unique symbol. There are no multiple edges with the same label leaving a single state. On the other hand, a non-deterministic finite automaton allows multiple transitions for a single input symbol from the same state. Therefore, given the current state and an input symbol, there might be several next states that the automaton can move to. This is where the term non-deterministic comes from. In the transition graph of an NFA, a single node can have multiple outgoing edges labeled with the same input symbol, each leading to a different state. The ability to represent both DFA and NFA makes transition graphs a versatile tool in the study of finite automata. By using transition graphs, we can visualize the behavior of both deterministic and non-deterministic automata, observe their state transitions in response to different input sequences, and gain insights into the recognition process of the languages defined by these automata. So transition graphs can be used to visualize both deterministic and non-deterministic finite automata. Now that we've covered the main components of a transition graph, let's summarize what we've learned. Nodes or vertices are the states of the finite automaton, each one unique and typically represented as circles or labeled points. Edges or arrows signify the transitions between states triggered by input symbols. They connect the nodes and signal the possible state transitions. The start state is where the automaton begins its operation, and accepting states or final states indicate successful recognition of a pattern or condition. Transition graphs can visualize both deterministic finite automata and non-deterministic finite automata. In the case of the latter, a single state can have multiple outgoing edges with the same input symbol, reflecting the automaton's non-deterministic nature. Understanding transition graphs is a crucial step towards mastering finite automata. So keep exploring, keep learning, and see you in the next video.